Hey, and happy Saturday, data science streamers. Fathead 152, let's go. Glad to be here with you on a Saturday for some new data science live streaming. My name is Carl, and I'm a data scientist in Silicon Valley, in case you don't know me already. And I'm going to talk today about machine learning and XGBoost, a very well-known algorithm for machine learning. And what can I say? I should start out with a little introduction. If you've seen my stream before, you might notice I've given up on my background, or on the virtual background, the virtual green screen. I've given up on it because if you saw my stream last week, there were multiple crashes with the Chroma Cam software. It was not fun. It was not pretty. So figured just go au natural. You can see my lovely office, or home office, I should say, because of course I'm doing this at home like everyone else. But anyway, enough talking about my streaming technology. Oh wait, I do want to say one last thing before I shut up about the streaming technology, is that I simplified my stack without using the virtual green screen from Chroma Cam, but today I'm using I got a Streamlabs OBS upgrade 1.01. So 1.01 is like a big milestone for Streamlabs OBS. But now comes the stability test. Is it going to crash on me? I don't know. A new version is not always good. But anyway, all right, without further ado, let me start talking about what I'm here to talk about. If you haven't seen my streams before, I start with some explanation, some background about the area of data science that I'm going to be talking to you about today. That's to level set so everyone kind of gets up to speed. I also play music the whole time. Right now we're listening to the copyright-free music streaming on Spotify. Let me know if the music is too loud or too quiet. I don't know. It kind of the level kind of varies on that stream. So anyway, let me know how the music goes, and I'm going to dive into the content and give you the background on what is churn. If you haven't heard it before, churn is subscribers, customers, or users quitting or unsubscribing or unfollowing or whatever it means in your context. The origin of the term churn comes from a metric called the churn rate, which is like the percent of your customers that are quitting. So you would do like a monthly churn rate or an annual churn rate, depending on what kind of business you're measuring. And I did a previous stream about measuring churn rates. So I'm not going to go into churn rate measurement too much today. We'll look at it a little bit. Then churn is now also a noun. You can say, here I'm saying it's a verb on the slide, but it's also a noun. I'll get to that. So you can say the customer churned, or I'm churning. I'm sick of Hulu, so I'm going to churn. And you can also, as I said, use churn as a noun and say, make a churn report for last quarter. Or you can even refer to an individual customer as a churn and be like, oh, that customer is a churn, they canceled. So that's like all the churn talk you'll get in the business if you're actually, working professionally fighting churn. So what is fighting churn with data? You saw that picture on the starting slide. I'll just mention it now at the start. It's the book that I wrote based on my experience as a chief data scientist at a company called Zora. And the book is out now. You can read here, prove it. Here's a hard copy of the actual book. It does exist. Took a while to come out, but very happy with that. And there's a discount code here if you want to get the book cheaper at my publisher's website. So the book is based on my experience fighting churn at a company when I was working at a company called Zora. And Zora is a platform that subscription businesses use to run their business. So a lot of companies you've heard of use Zora. You probably never heard of Zora before I told you about them. Like Zoom, you can see, is on this slide on the bottom left. They are probably the most well-known company on Zora because Zoom is now also a noun and a verb. You can have a Zoom and you can Zoom someone. But Zoom manages their subscribers, their customers, and their subscription plans and billing on Zora, as do many companies. And so it was working on Zora that I got I spent so much time doing churn analyses for different companies that I don't know. That's how I came to write a book about churn. So let's see. Why learn about churn? Well, if you're here with me, you probably already know, but I tell everyone churn is the most common data science problem in the world because every company has a churn problem. But there's a lot of special tips and techniques that'll make your churn analysis go better. Also, it's a great way to learn data science foundations because what I teach is going from the raw data that you get with churn in a churn scenario all the way up to the analysis. And actually, I said we're doing machine learning today. We're pretty much at the end. We've gone through in my stream all the subjects of an entire churn analysis, and that's what the book goes through. So we're up to chapter 9 in the book at this point. But it starts out with the raw data at the very beginning. So maybe we should look at the raw data real quick. Well, okay, after this slide, we'll look at some data. This is the slide to tell you what is data-driven churn reduction. Well, that's what fighting churn with data is really about. So data-driven churn reduction means actually, doing things which are going to reduce churn on your product, like make a product that people love, because that's the best way to have low churn. But you can use your data to figure out what's the best parts of your product. So that's fighting churn with data in your product. You can also market to your customers by targeting them with engaging communication, emails that people really want to open, if you can use your data to figure out what people really want to know about. And you can also make sure your customers are successful and support them with training and help when they need it. And the data can really help you figure out what customers are having trouble without waiting for them to ask you for help. That's the key. And lastly, there's your company's sales and pricing. You want to right-size your product and plans without giving discounts, what I tell people, because discounting, many people think of discounts when they think of churn and reducing churn. You threaten to churn and the company offers you a discount. That's the way it works, right? Well, if you're a company, that's not so good. It's better to give a tiered pricing structure where people can get value without you giving them a discount. Because once everyone knows about, the discount churn trick, it just undermines your pricing. So that's what data-driven churn reduction looks like. And that's really the goal of fighting churn with data. All right, so without further ado, I think that kind of explains the basic background. Let me know on the chat if you have any questions, need any more info about anything you've seen so far. And without further ado, let's look at some data. I say, where's the data? Now this is actually what we're going to look at today is all simulated data. Sorry, it's not real data. Oh, actually, here's already some data I had loaded into the SQL editor. So there's a data schema, a database that goes with this training, and the foundational data in it is events. So this is looking at a query. Here, I'll run it again. It's an event table joined on an event type table. This is what's going on in this query. So the event type table gives you these names on the right. So the simulation is a pretend social network where you've got customers. They all have an account ID. So the events represent customers that you can track over time. Actually, here, let's like enhance the SQL a bit and say where account ID equals 939, that first customer. We'll look at all his events. So we see that this customer has posts, viewed some ads, more posts, they disliked something, etc. So these are all events from a simulated social network where the event tracking allows you to know what the customer is doing over time. And that's necessary to understand the behavior of the customer and use all these techniques. But remember, this isn't like stalking your customers on the internet. This is tracking what they do within your walled garden of a product or service. Now, this is a very legitimate kind of way to monitor your customers because really you're monitoring the health of the service. And this is all anonymized data. So events like this form the basis of fighting churn with data. Well, there's one other kind of data we need, which is subscriptions, because this is supposed to be a modeling a subscription service. We've got a subscription table, Let's see, let's look at that same customer again. We looked at account 939 equals 930, whoops. So this will show us that customer's subscriptions. So they signed up on January 1st. Their subscription is $9.99 a month, and it looks like this customer lasts until June 1st. Actually, that's when the simulated data ends. It's only 6 months of simulated data. So this customer actually never churned in this simulation. But you can see each subscription gives a start date and an end date that covers the subscription at that period of time. And in this simulation, there's only one price. Last stream, we were looking at a simulation with more varied pricing structure. For this week, we're not focusing on the price, but that's part of the analysis that you do. So, subscriptions and events are the basic data that you use to understand what your customers do and fight churn, because the subscriptions are telling you who churns when, who signed up when, and then the event data tells you what they did. And now what we do is, well, I'll just get into it. We do an analysis. From the events, you're going to create a data set. Well, actually, this here will show you, now I should mention, before I get into the weeds too much, this is where you can get the code for today's stream. And all the code for the book, Fighting Churn with Data, of course, is open source and free. So today we're actually going to look at code in a branch. I made a special branch for this stream which contains some additional information about XGBoost. Additional code for XGBoost, I should say. I have a certain number of code examples in the book for XGBoost. I felt like I needed a few more for this stream. So if you're actually trying to follow along this stream, this is the branch you should get. I don't think I'm going to merge this into the master branch. We'll see. But anyway, you clone this repo, get that branch. You'll need Postgres database and Python to follow along with the code in the book and do, all the code exercises. You actually run a data simulation to get the data that you'll analyze. So sorry, if you're just downloading this right now, the simulation takes about 15 minutes to run. So it takes a few minutes to run, but then you'll have everything you need and to follow along with this. Although I mentioned earlier, today we're going to be looking at code in chapter 9 of the book. So we're nearly at the end of the entire book. There's only 10 chapters. So to have the data that you need to do this, you kind of need to go through the first several chapters. I should think about maybe making a downloadable version that has the earlier chapters in case you don't want to follow through. But for now, you'll have to run the data simulation and get up to chapter 9 where we will move ahead. So if you've done all that, then you have a data set. And this is a summary of the data set, which is about the social network service. So I said earlier that we start with events, and events are the things that customers do on the service, and you track them in real time as they're doing it. And then you combine the events into metrics or measurements of the customers, and then you take the metrics or measurements and put them into your data set. And I went through all of this in previous streams. So if you look back in my old stream history, look for the one on data sets if you want to find out how we make the data set. Let's see, I can show you what a data set looks like. I have it open right here in Microsoft Excel, which is also a handy data viewer when it doesn't crash your stream. Although I always blame Excel for crashing my stream. I don't think it's really Excel that crashes my stream. I think it was the virtual green screen software ChromaCam that was crashing me. But anyway, so I was saying what a data set looks like in case you've never seen one. In each row, we have one customer shown by their account ID, and on one date, we observe them and we take a bunch of measurements. These are based on their events, but these are actually the measurements we take are summaries of the events. So this column has the measurement like per month. So for customer 56 or 107, they had 8 or 9 likes per month, on these days. These guys had no new friends, and they have a whole bunch of other measurements. But this is what the data set looks like. This particular data set has, I think, around 20,000 rows. Yeah, 25,000 rows. So 13,000 unique customers that have all been using the service, and some of them churn and some of them don't. And so the summary of the data set is back here. Now this is worth looking at because some of this is going to come up again when we do our machine learning prediction and analysis later. First thing is the churn row here, 5%, that's showing the churn rate on this service. So 5% monthly churn, it doesn't sound that bad, but that's actually kind of like 50% churn per year. You know, Netflix and top-line services have churn below 10% per year. So this simulated social network has kind of mid-range churn. 5% is not good, but I've certainly seen a lot worse than 5% per month. Okay, we have these metrics that we made, as you were seeing before. Like per month, new friend per month, post per month. Those are the basic metrics which simply count the things that the customers did on the service. I went through all the code to create these metrics earlier and the code to do the data set. This summary is created with listing 5.2. If anyone on the chat is jonesing to see some code, I've been talking too long, let me know and I can run this listing. Listing means it's a segment of code from the book. So I can run this if you want, but otherwise I'm just going to talk through it and we'll get into some code soon. So there are also some metrics further down which are more complicated. They're not simply count per month. This one, ad view per post, is the ratio of the ads viewed to posts made. And reply per message is how many replies you make per message that you receive. So those are more complicated metrics based on more than one type of event. And at the very bottom, there's also some other kinds of metrics like the percent change in the number of new friends and the days since your last new friend. Those are also kind of nonlinear, more advanced measurements that go into the data set. Now, you also might have heard of features. Features means one of these measurements or metrics, and a feature is data science or statistician language for a measurement of your data. And I don't know, there's some history to why they call it feature. I'm not sure. I don't usually call it features myself because people in software companies might get confused and think you're talking about software features. But so this is a summary of what's in the data set. It's telling you things like the average value. So the average likes per month is 97. The average post per month is 42. This is a pretty busy social network. People who use this social network really use it a lot, if it were real. Ad views per post, the average is around 1.6. So people generally see more ads than they make posts. That's probably believable. A good metric here would be posts viewed. They don't really have that one. Post per month is like, how many things you've been posting. But anyway, so a summary like this is a great way to learn about your data set. And I showed you what the data set looked like already. Here's that data set. If you missed it before, it's just a bunch of data, one row per event or per customer. All right, so now let's get into some prediction. Previously on my stream, we looked at using the logistic regression model to predict churn. And I explained how logistic regression is a probability model based on a multiplicative relationship between the metrics that we were just talking about and a set of weights. And then you use this S-curve shape to convert from the measurement of engagement or the likelihood the person will stick with a service into the actual probability. We also looked at this chart on the right, which shows you the cross-validation of the logistic regression model. And in this case, the cross-validation consisted of checking one parameter and basically using it to get rid of the extra weights or coefficients. This bottom chart shows the number of weights or coefficients being reduced and you reduce them until the accuracy in these top two charts starts to decrease. So we went over all that. We're going to go over these accuracy measurements again in just a few minutes in case you are not up on them. The top accuracy metric here is the AUC, or area under the ROC curve. If you can't see it, it's just hovering under 0.8 there. And the middle accuracy metric here was 4.5, and that's the lift, the top decile lift. I'm going to explain these again in just a minute, but first we're going to talk about predicting churn with machine learning. All right, so predicting churn with machine learning. What is machine learning? Many people not familiar with this subject may ask that. Machine learning is an algorithm which makes a prediction by learning from data. So you make predictions about who's going to churn by learning from the data and not by applying logic or rules that you program. Because one way you could predict churn would be like, predict that everyone with fewer than 20 posts per month is going to churn, and you could just come up with that rule and write it down, and that could be your prediction. But that's not learning because you made it up yourself. An algorithm should learn it from the data for you, for it to be machine learning. Now, that sounds a lot like the regression algorithm that we learned previously. So the other key characteristic for an algorithm to be a machine learning algorithm, I would say, is that it has to not be the regression algorithm. And you would say, why isn't the regression algorithm machine learning? And I would say, well, it's kind of older. It's not a new algorithm. So machine learning algorithms were all invented in roughly the last 30 years. So I don't know if anyone in the chat has a, strong opinion about this, but I would say a good way to divide, machine learning from statistics or non-machine learning algorithms is, is it new? Is it invented in the last 30 years? And if it's, relatively new, then you're going to say it's machine learning. And older algorithms like logistic regression, you would call statistics. Logistic regression has been around for decades. Even the version of logistic regression that I taught in the stream, which is ridge regression, that's a more recent and advanced kind of regression. But it also, I believe, is around 50 years old. Now, XGBoost, I think, is just around 10 years old, and that's what we're going to be learning yet. So that's just what is machine learning. And why do you use machine learning? Well, I'm not showing it here, but it actually will tend to make predictions more accurately for you. So, good reason. All right, so I don't know if no response on the chat from my explanation of what is machine learning versus statistics. I guess people consider that an okay answer. So let's see. Here's an example of a machine learning algorithm applied to churn. And this is called a decision tree, and it's one of the most common approaches to machine learning or prediction. And the idea is, like shown in the picture, that you're going to make a prediction with a tree of decision rules, and each decision rule has a cut point. So let's say we start out with this customer at the top, and we want to predict if he's going to churn or not churn. So maybe you run your algorithm and it produces the tree. That's the first thing to know. So the rules in these trees are going to be created by an algorithm. And I'm actually not going to go into the details of these algorithms because I'm not an algorithm teacher. I'm a churn fighting teacher. So I'm going to show you how to apply this to churn, but not get too into the weeds of how the algorithm works. So this is a hypothetical tree that might come out of the algorithm, and the first node of the tree may be, did this person have more than 2 new friends? And if the answer is yes, you go down one path, and if the answer is no, you go down another path. And then you might get to another node in the tree, and it will be, how many ads did they watch? Less than 20 or greater than 20. This is assuming we're using these, metrics based on the social network. And if the answer is no, then we go down to this other node where it might say, how many messages did they send? And then based on the answer of these questions, you get to the terminal node of the tree, and then each terminal node will give you a prediction of either churn or retention, depending on, how that person traversed the tree, how that customer traversed the tree. And this is an okay machine learning algorithm. The truth is decision trees are not very state-of-the-art. They're kind of Nowadays you wouldn't really use a decision tree by itself because it doesn't give you the best predictions. And although it looks pretty easy to understand in this simple example, real decision trees are much more complicated and are not very easy to understand. So you don't actually use decision trees for machine learning. And don't worry, we're going to get to some code soon. Maybe I should go back and run that dataset statistics query so I get some code in. But don't worry, code is coming, talk is ending. Now, this is an introduction to XGBoost, which is the algorithm we're going to start running in just a minute. And an XGBoost stands for Extreme Gradient Boosting. And this is actually an ensemble of trees, or a grouping of trees, is what they call it. It means that the algorithm doesn't just make one decision tree, like we were showing in the last slide. We actually make a whole bunch of decision trees. And then instead of going to one tree and saying, did they churn or not, it actually takes a weighted vote from all the trees. So XGBoost is actually kind of like a democratic algorithm in that you make a bunch of trees and they take a vote, except it's an elitist democratic or an elitist democracy. It's not an equal democracy in the XGBoost vote because the votes are weighted. They're not only weighted to give the best trees the most weight, the trees are actually created to correct the errors that the other trees make. So the algorithm starts out with one tree, maybe there's one here on the top left, and after running that tree, it sees what customers, this is talking churn, it would see what customers the first tree made mistakes on. And then the second tree is actually going to be created to correct the errors of the first tree. And then the third tree will be created to correct the errors of the first two. So each tree is added and added with a weight and also created to correct the errors of the earlier trees in the ensemble. And that is why XGBoost is such a powerful and accurate machine learning algorithm. It's because it has it uses the ensemble principle, which is a very powerful principle in machine learning, which is to combine more than one predictor. There's a great lesson for real life too. You want to make the best predictions in anything. Don't just ask one person. Get input from lots of people. And this takes that principle to a higher level even by creating the ensemble members to correct the errors of the earlier ensemble entrants. Now, I'm not going to go into the details of how XGBoost works because, like I said, I'm not an algorithm explainer. If I was a great algorithm explainer, I think I'd be a professor, or maybe I would have stayed in academia. But I'm more of a churn fighter, an applied data scientist. So we're going to look at using this rather than explaining how it works. So I think without further ado, we can finally get into some code. All right, let's look at fitting our first XGBoost algorithm. And as I said earlier, this code is actually not in the master branch for the book. I put in a few extra XGBoost examples, like the one we're going to look at right now, and it's in this branch 2021-0401. It's my April Fool's branch, XGB Extra. So let's go to the code and look at listing 910, where we'll do our first XGBoost fitting. So if you download this code, or if you have downloaded it, you'll see there's a folder called listings, and this is just, I don't know, I picked up that listing lingo from the book publisher. The book publisher calls every piece of code a listing, so that's why I call it a listing. So 910, assuming I'm in the right branch, is right here. So this is our basic XGBoost fitting algorithm, and I called it XGB fit, appropriately enough. And if you're new to data science or machine learning, I should explain that fitting means learning the algorithm. It's when the algorithm does its learning. They call that, fitting. It's also called training. So I don't know, there's a lot of data science lingo you have to get used to. So I'm going to put a breakpoint here so we can step through it. And I'm going to go to the configuration. Now these are the configurations you run to run the code in the book. And if you've gotten up, there's instructions about how to set all this up. If you go to the GitHub repo, it has everything in the README. I should show that in a minute. But it'll tell you how to set all this up. There's a program, run churn listing.py, which is the wrapper or script which runs all the individual listings. And then you give it parameters of the chapter and the listing number that you want it to run. And I'm going to use several of those during the stream today. So now I've got my breakpoint, and we will finally fit our first XGBoost model. And we'll see how it does and what it does. So the first thing we have to do here is load the data. So I have a function from an earlier chapter that loads my data. You can see this is from listing 8.2 prepare data. So we can step through this one just for the first time we've encountered it. And you'll see what happens, because this is pretty standard. I'm basically just going to load previously saved data from a file. This is the same data we were just looking at. So on this line, I checked that my path exists before loading it. And then I use pandas, which is the data frame package in Python, pandas, to load the data into a data frame. All right, so now this is my data frame. We can actually check it out. And you can see that this contains the same data. Sometimes this crashes my computer too, but it's all behaving nicely today. So this is the same data we were looking at just earlier in the stream. It's got the is churn column telling us who churned and all the metrics we were looking at. So this is exactly the same data we were looking at earlier, but now it's in memory in Python. All right, so to prepare the data, we really just have to split off the y variable here, because this is the outcome of the prediction. And we're also going to convert it to an integer, because that's just what XGBoost wants. So in the file, it says true false, because churn is a binary outcome. It's either true or false. It happens or it doesn't. So here we're going to split off the y value to keep it separate. There's this variable here. This is actually an option to predict as retention or as churn. And by that I mean, well, it's a binary outcome. So it's just a question of what sign you choose. Do you want to predict retention or do you want to predict churn? It's like glass half full or half empty. In this case, as retention is set to false, so we are not predicting retention. We're going to predict churn as the outcome. Retention is convenient to predict when you're doing a logistic regression. That's why that option is there. So we got the outcome in the y variable, and now we're going to drop the churn from the data and get the x. And that's all we do to prepare the data. This is very common, in this kind of situation where you have a data set, but you have one file that has both your prediction variables, which is the metrics or features, and the outcome variable. If you're a statistician, you would call those the independent variables, which are the metrics or features, and the dependent variable, which is the outcome. But anyway, so now we've got those separated out, and now we create the XGBoost classifier, and this is coming from the XGBoost package here. Looks like I have a few extra packages there, but we'll just ignore that for now. So we create an XGBoost classifier here, and we're using the objective binary logistic, which means we're trying to predict the probabilities of churn or the outcome. And these other parameters are just some defaults. Don't worry about the other parameters for now. And so really this is all there is to it. So I created the object, and now I call model.fit. And as I told you, fitting is what they call training or learning. And that was it. It just ran. So we just fit the XGBoost model right now. So the next thing we're going to do is save it. And this is a standard Python saving with a pickle. A pickle is an object storage in Python. And if you are familiar with the English language, pickle means like a preserved vegetable. So pickles, typically pickled cucumbers, are what people refer to as pickles. So anyway, so we're going to save it with pickle dump, and we're going to reuse the same model later. And I made the name for the pickle by taking the data set and replacing .csv with XGB model. So that's how we're saving things out. And this just prints that it saved the pickle. So now we're also going to make some predictions with the model. And this, but because we've already fit it or tuned it or trained it to the data, so now we call the predict proba function. And predict proba is for predicting the probabilities. So we're predicting the probability of churn. We've actually, that was it right there. We've actually also predicted the probability of retention. If you look in this variable, you'll see we have column 0, which is the probability of retention. You can tell because they're higher numbers. And column 1, which is the probabilities of churn. And these add up to 1 because churn is 1 minus retention because it's a binary outcome. So that's what we get when we do the prediction. And now I'm going to save the predictions in a data frame. So this is again using pandas to create a data frame. Save the predictions. And lastly, I'm going to look at the predictions in a histogram. A histogram is a plot of them. And we're going to do a few different histograms during the stream today. And so just this once, I'm going to step through it and show you all how to create a histogram. And then we'll look at it later. It's very easy to create a histogram using these tools. So this is again a function from a previous chapter, forecast histogram. And it is as easy as using matplotlib plot. That's again this package up here. Import matplotlib pyplot as plot. So we create a plot. And then we just call the hist function. My plot showed up over there, showed up in my other window. I'll just put it here where you can see. So now we just call the hist function, which is a built-in matplotlib function. Okay, so that's our histogram. And the rest of these lines are going to put the labels on the histogram and then save it. So here go some labels. I'm just going to let this run out, and then we can look at the histogram that was saved. Because in my code, all the results get saved out to a local folder. And that's because usually in a business context, you're going to want to look at these things and share them with people. So let's see. This is the folder where I think it should be landing. Yeah, and here's our new histogram that we just created. Let's see. So what we see in the histogram is each bar represents customers that have a churn probability in that range. So the first bar is people with churn probabilities kind of like 0 to 5% or 0 to 0.05. And we've got more than 20,000 customers have that churn risk. So most customers have less than 5% churn risk, which actually makes sense because remember the overall churn rate is only around 5%. So we see a small number of customers have more than 5% churn risk, first represented by this bar, which is kind of like the 5 to 10% range, and this is like the 10 to 20% range, and then there's a very small number of customers in a long tail that have much higher churn probabilities. But most of the predicted churn probabilities are just 0 to 5%. Now why? Well, this has to be the case because, remember, the average churn rate is 5%. So if the average churn rate is 5%, the average probability of a customer churning has to be around 5%. Because a lot of times people, after I do a churn analysis or predictions, they'll be like, oh, where are the customers who have 90% likely to churn? Well, there's not that many of them. It looks like there's a few way down here. You can't even see the line, but I think there might be a few. There's a few over here. I don't know if you guys can see these little bumps. Okay, it looks like there's a few customers with kind of like 80 to 80% churn probability here. I guess that's as high as it goes. But the reason there aren't that many customers with that high churn probability is, well, they would have churned already. Like any customer that's 90% likely to churn probably churned last month. In fact, they were 90% likely to churn last month. So they don't hang around too long. So the real product or service, you're going to see churn probabilities forecast to be around the average churn rate. And that's the main thing I wanted to point out on those predictions. So we've also saved the predictions in a file here and the data from that histogram. But I think that's kind of good for now because we've already seen how the XGBoost model can be fit and then it can be able to predict the churn probabilities. But now there's more you'd probably want to know, which is, well, what is the model predicting? You know, why are customers at risk versus not at risk? And that was something we were able to get from the logistic regression model pretty easily. So how do we understand XGBoost? This is actually a very exciting section for me to be presenting to you, or at least it's exciting to me, because I actually just learned this method very recently, and I'm going to admit I am behind the times, because this method was actually invented in 2016 and started to become popular in 2017, 2018. Now, I am late to the game. I only learned this method a few months ago, and I learned it after I had written the book, so I wasn't able to put this into the book, sadly. But here I am. I'll live stream it, and I'm including it in the code, you know, for the book. So anyway, so this is understanding XGBoost with a method called the SHAP method. And SHAP, S-H-A-P, stands for Shapely Additive Explanations. And this is what the SHAP method is all about. As I mentioned earlier, I'm not really an algorithm explainer, so I'm not going to go into the details of how this algorithm works. I'm going to give you a high-level explanation, and then we're going to use it and look at the results. So that's the game plan here. So the question you're trying to answer here in understanding a machine learning algorithm is how much does each metric or data feature or variable contribute to the prediction? And you'd like to answer that question both in general, and you'd also be able to like to answer that question on individual examples. So for example, if you want to know why a single customer has a high churn prediction, you can answer it. And you also want to know overall what are variables that contribute, you know, to having a high or low, you know, churn rate. So let's see. The answer from the SHAP method is based on a game theory analysis of the coalitions. So the SHAP method is from game theory, and I'm not a game theory expert. But the idea is it's a way of looking at games to see how much each player contributes. And to do that, it analyzes how the outcome would have varied if certain players were not involved or were not present. So it actually looks at the features or variables in your data as different variables. Hold on, I'm going to try to turn down the light a little bit. I'm just noticing that my a little bit too bright in the video. I'm wondering, does that give me a more healthy glow on my skin? I can't really tell. Anyway, so the SHAP method looks at the variables as if they're players in a game and analyzes how much each one predicted to the outcome, which in this case is the prediction. Now, it's a complicated method, and when I said you want to look at different coalitions, that actually implies that you're going to look at different subsets of variables or subsets of team members. And there's actually a huge number of possible subsets. However, the key contribution or the key breakthrough in 2016 from Lundberg and Lee was an exact solution to using SHAP explanatory variables for machine learning for tree-based methods like decision trees or XGBoost. And that is in this paper I'm showing here, A Unified Approach to Interpreting Model Predictions. Now, what do these explanations look like? I think we should look at an example, and this will be another new listing, which is, this is actually in the master branch. I actually added this to the master branch of my repo last week because I thought this was so good. Everyone who uses XGBoost should start using this. So let's look at an example of the SHAP explanation of the XGBoost algorithm that we have produced. So we'll go to listing 9.8. Let's see. I'm going to close up these helper functions. We don't need to look at the XGBoost fit model because we've already fit it. So here is the code for explaining a SHAP algorithm. And I think I have a configuration to run it already. Yeah. So just chapter 9, listing 8. And now we will go and we will hit the breakpoint and we will see what it does. So the first thing we do, of course, is to reload the XGBoost model that we already saved, because that's what we did in the last listing. And this listing assumes you've already got an XGBoost model ready. So first we check that the path to the model is valid, and then we use the same pickle package that we used to save the model, we're going to use to reload the model. So here is the XGBoost model reloaded, and now we have an XGBoost model object. You can see it's an XGB classifier. There's not too much, well, there's a lot to see inside, but since we don't know the guts of how the model works, better not to get in there. Now, to use the SHAP explanatory model, it's actually based on data. So it actually looks at points of data and looks at how the model would have predicted for them. So the next thing we have to do is reload some data. And so now this is a data set of customers. It's actually not the data that we were looking at before. This is what I call the current customer data frame. We looked at how to produce this. So this is a data frame of all the customers at one given date at the end of the analysis period. That's fine to use for this purpose. So then we create the SHAP explainer, which is an object in Python. Now for this, I should mention, we have the SHAP package. So simple enough. You want to know where to get the SHAP explanations for machine learning in Python? It's in the SHAP package. So we create the explainer object, giving it the XGB model. And next, we call the explainer on the data set that we're using. And this is just like a no-name method, apparently. You basically, I mean, it's a little confusing here, actually. This is the constructor. And now we're just, the explainer, the main thing it does is explain. So they just have that as an operation where you pass in the data set. Now we have the SHAP values, which are an array of contributions to the predictions. And we're actually not going to look at them here. We're going to visualize them. So we call the summary plot function, and this is what it looks like. It opened up in my other window as usual. And as usual, I'm going to save this, and then we'll look at it in more detail once we finish running the code. So I'll explain what that cool looking plot is in just a second. I'm just going to run out the code and save it. And then we will look at the version that I can load right here that we just created. So this is an example of a SHAP summary. I actually don't even know if I'm pronouncing it correctly. It may be shape because it's shapely. So maybe I should be saying shape. I don't know if anyone in the chat knows the SHAP or shape method for explaining machine learning. But we are looking at one now, and let's zoom in a little bit. So each row gives you the explanation contributions for one variable. And each point, actually I'd better zoom out first to show you the whole thing. So on each row, we're going to look at the contribution of one metric or feature or variable. Each point represents the contribution on one example. So we're going to look at all the contributions from message per month to all the examples on one row. So each example is like a customer that you're predicting on. Now, whether message per month is low or high for that example is shown by the color. So these red points here are those customers that had a high message per month. And these blue points are those customers that had a low message per month. And they stack up when a lot of customers had that value. So you can see the thicker stacks in the middle close to the midpoint of the feature value here. Now the contribution to the churn prediction is shown on the x-axis, and the zero vertical line is like the neutral, no contribution. So what you can see in this is a combined summary of how all the different metrics contribute to all the different predictions in a pretty interpretable way. So this is saying basically that those customers with high message per month, shown by the redness of their point, have negative impact on the model output, which is the prediction of churn. Also, customers with high new friend per month, shown by the red and purple. Ooh, Insipidity, first comment or question of the day. Thank you for joining. Good morning from Singapore. Wow, and I'm so glad that someone in Asia is watching. What time is it in Singapore? It must be like 7 a.m. or really early. Anyway, you brought the book some weeks ago and using it religiously. Wow, on your Churn project. Has it worked? Wow, really glad to hear that you've been making good progress. 5:50 a.m. Oh my God, Insipidity, thank you. And I hope I'm pronouncing that right. Thank you so much for waking up early to join the stream. That is awesome. And my heart is touched. And I hope you find this useful because this is not in the book, actually. I hope you've been seeing. This is extra, not in the book, and it's really helpful for explaining XGBoost. As I said earlier, when I wrote the book on it, I was writing in the book about XGBoost. I didn't know about this method, so I didn't include it. Sadly, I only learned about it a few months ago, after the book was already kind of a done deal. Anyway, back to my explanation, and thank you for the warm welcome, Insipidity. So, going down to the next row, here we can see a feature or metric which is actually negative in the sense that it increases churn, which you can tell because all the high values of add view per post are on the right. So those are increasing the model output, which is the churn prediction. And you can pretty much see, it gets a little bit confusing down here, because then when we look at add view per month, it seems like high values are both associated with more churn and with less churn. And that's because this is a decision tree model. It's actually an ensemble of decision trees. So it learns complicated relationships. But you can basically eyeball this chart and see what kind of contributions each metric or variable is making. You can also see which are the most important metrics or variable because they're at the top. So message per month is at the top because this shape explanation considered this to be the most influential variable. And unfriend per new friend is listed at the bottom. It's shown to be the least influential. And you can actually see it's the least influential by noting that the contributions are closer to the center. So at the top, the contributions go all the way out, to these extremes. Remember, the x-axis is the contributions. This unfriend per new friend is making a narrower range of contributions. And you can also see the customers are more clustered near the center in the influence on this one. So these are all the ways in which the shape explanatory factors really make XGBoost models much easier to interpret. Now in the book I actually said, don't even try to interpret XGBoost. Just look at the logistic regression for interpretation. But I didn't know this method when I wrote that, and now I'm like completely converted to using this to interpret XGBoost. Now it can also do explanations of individual examples, which I didn't really demo. I didn't prepare that. I got other stuff to do in the rest of the stream. Maybe we can do that later. But you can also use this method to look at an individual prediction and see, say, for one customer, how much does each metric contribute. Okay, but so this is showing you an illustration of how the XGBoost predicts. You can see for all these different metrics how they typically contribute to the prediction, what's the most influential, the least influential, which those are really the things that you want to have an explainable machine learning model. So 2 thumbs up to the shape method. I'm so glad I learned it. I'm so sorry I didn't learn it before I wrote the book, but hey, what are you gonna do? You live and you learn, and that's one of the great things about being a data scientist, that new methods are being invented all the time. I told you earlier, XGBoost was just invented about 10 years ago. Pasty Tato. I don't know why I'm here. I must hate myself to be learning about work during a weekend. Ha 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 ha. I'm hopeless. Guess I'll stay here. Yay, Pasty Potato. Thank you for being part of the data science team. I don't know why I'm doing this on the weekend too. I guess because I don't have a chance to do it during the week, and I want to do it. So it's just an available time for me. But Pasty Tato, you could just watch this stream later at work. That's another. But if you want it live and ask a question and have me actually talk to you and hear your name, then yeah, well, cool. Thanks for following, and glad you made it to a live stream. And this one is a very good one, I think, like I said, because I'm covering material that's not in the book. But anyway, let me get back to what we're going to talk about next. So that was explaining XGBoost. We've actually got a lot more to do in this stream. And some of you who have data science experience might know where we're going next, and it's to accuracy. So not only do we want to be able to explain our predictions, we want to know how accurate they are. It's a very big obsession in data science and machine learning, as you must know. So when we talk about accuracy, there is both the general meaning of accuracy and the specific meaning, or a specific meaning. And the general meaning of accuracy is just how good a match is your model to reality, right? That's what accuracy means. Sorry to ask this, no stupid questions, but have you covered feature engineering in any of your previous sessions? Yes, Pasty Tato. I spent actually a few weeks on feature engineering, and we're going to have some about feature engineering later in this stream, about 20 to 30 minutes from now. We'll be looking at some results of feature engineering, and actually doing the feature engineering is in all older streams. Like chapter 3 and chapter 7 are the feature engineering chapters, and the streams are labeled by chapter. Okay, Insipidity. Will readers be able to find this code about SHAP values added on the Git repo? The answer to that is yes. I'm sorry you missed this earlier, Insipidity, but I can skip over to that. We are actually using some of this XGBoost code, I should mention, is in a branch. Maybe I should just show you all where this is. So there's extra XGBoost code in a branch, 2021-0401 XGB extra. But the SHAP code, I already put it in the master branch. I'll just show you guys. Real quick detour to GitHub in case you've never seen it. Let's see, getting to GitHub. This is my website, and I have a link here. Well, no, I have a link here to get to the GitHub repo. So in the master branch, I have already put the SHAP explanation, because that was just so good. I had to put it in the master branch. 9.8 is XGBoost, and there's also a logreg version, 9.9. Some of the other code that we're looking at today, though, you're going to have to go to a branch, XGB extra, and that's where you'll find these later listings, 10, 11, 12, 13. So that's the quick detour into the status of the code. So back to the master branch, it contains the SHAP explain examples, just a couple. All right, but next we were going to talk about prediction accuracy. I think that covered all the questions. So we want to talk about accuracy, and there's both the general meaning and the specific meaning. So first, let's look at the specific meaning of accuracy, which is the standard accuracy measure. And the way, I'm sorry for those of you who know this already, but I need to cover the bases for people who don't. The accuracy measure, the specific definition, means that you predict who's going to churn, meaning you assign them a yes or no, and then you look at what percent were correct in the specific formula shown here. True positive plus true negative divided by total. Now suppose this is the increasing risk of your customers, and if you look closely, you'll see smiley faces here, frowning faces here. And let's suppose we predict who's going to churn by drawing this line and looking at the 5 most likely customers to churn, and then we say, these are the 5 who are likely to churn. And then the red slashes here show who really churned. So we said these 5 would churn, and we were actually correct on 2 out of 5. So that gives us 2 true positives. And then we said that these 45 would not churn, and 3 of them did. So that means we had 42 true negatives. So in this case, our accuracy is 88% because we had 2 true positives and 42 true negatives out of a total of 50 customers. This is for churn prediction. So that's how we get 88%. Now, is this a good measure of accuracy for churn? And I'm going to say no. This is actually bad. I mean, 88% sounds like good accuracy, but let me show you a better way to get accuracy for churn. I'm going to cheat on accuracy for churn, and this is how you do it. I predict that no one is going to churn. That's my prediction. No churns. That's why I haven't drawn any line. Remember, on the last example, I drew this line, and that was how I said my predictions of who's going to churn. Now I predict no one's going to churn. Now, what's my accuracy? It's actually 90%. Why did I get 90% accuracy when I didn't predict anyone would churn? Because remember, the accuracy measurement is true positive plus true negative divided by total. Because I predicted that no one was going to churn, I had 45 true negatives out of 50. Now I had no true positives, true, but I had 45 out of 50 true negatives, and I got 90%. But that's cheating, because I didn't make any prediction. I just said no one's going to churn, and I got 90%. Now that works because churn is what we call an unbalanced problem. So churn is unbalanced because there aren't that many churners. So let's talk, so this is my example to show that the standard accuracy measurement is actually not a very good one for churn, and you should not use standard accuracy for churn. You should use a different accuracy measurement, or a few different accuracy measurements that I'm about to tell you. And the first one we're going to look at is called the area under the curve, or area under the ROC curve, and it's called AUC. Now, as usual, I'm not going to go into the algorithmic details, but I'm going to try to explain it to give you an intuition. Now, the way you do the AUC accuracy measurement is you take all the non-churns, shown here on the left, and you take all the churns, and then you look at what your model predicted for them. So did the model predict what was the risk? So it's actually a probability. So you take a churn, a true churn, and a non-churn, and you look at if the model predicted higher risk for which one. And if the model predicted higher risk for the churn, then you say that was a correct comparison. And if the model predicted higher risk for the non-churn, then that was an incorrect comparison. Now you actually look at every pairwise comparison between the churns and the non-churns. So in this case, if we had 5 churns and 45 non-churns, we would have 5 times 45 comparisons. I guess divided by 2, because the order doesn't matter. But so you do a lot of comparisons, and you look at what percent of the time the churn had a higher risk than the non-churn, and that's your AUC. And this is a much better accuracy metric for churn, well, for a few reasons. One, because you can't cheat like in the standard accuracy metric. This one you can cheat because of the imbalance. But in this case, you can't cheat because every churn is going to be compared to every non-churn. So you make full use of all your churn data. And it's also a good measurement of accuracy for churn because it's based on the probabilities. And actually, the probabilities for churn that you come out with are more important than the predictions. Because usually in a churn use case, but the predictions, I mean like the binary true-false predictions. Usually in churn use cases, you want to do ranking. And ranking, you're looking at the probabilities. All right, so I think that's enough explanation of the AUC, hopefully. Maybe not the best explanation ever. Let's look at some code, and let's look at, oh, I had some animated arrows I forgot about. Let's look at some code and look at doing an AUC calculation with our XGBoost model. This will be a pretty quick one. Let's go to listing 911. Now this one is not actually in the book. In the book, I actually make a similar example with logistic regression. So I do a simple example of an AUC calculation with logistic regression, and that's why I didn't do it again with XGBoost. But because in this stream, let's see, I think I actually need to to find a new listing here. I mean, a new configuration. Let's see, this is XGB AUC. So chapter 9, listing 11. So like I said, in the book I do a similar example with regression, but today we're doing XGBoost. So that's why I made this new listing. So I'm just running it, and guess what? We start out the same way as the last one. We load the pickle from the model that we already saved. Next, we open it. Then we use the same prepare data function, which I demoed earlier in the stream. So sorry if you just joined. We don't want to demo this again. It would be boring. What we do, we also looked at the predict proba function as well, which gives us the predictions from our saved model. So I'm just going to go straight through this. Now, to get the AUC, we actually just use this function. Where'd it come from? It came from sklearn metrics, ROC AUC score. So, we call it, and we get our output. You can actually see here, the AUC is 0.995. Wow, that's really good. Is it good? I ask you. So the listing ends, I think, just printing out on the console what the AUC score was. So that's all that happens with this one. So it had 0.995 AUC. And remember, AUC only goes from 0 to 1, so that's really good. So now let's talk about, and if you're a data scientist, you already know this, you might be suspicious of 0.99 AUC. Why? Well, here's my explanation of how good is good for things like, AUC scores. Whoops. Adjusting the chat size there, never mind. So how good is good for AUC? Remember, AUC is the percentage of times that you ranked the churn as a higher risk than the non-churn. I mean, your model did. So 0.5 is random guessing. So if you get an AUC around 0.5, then your model is really no good. It's random guessing. If you get less than 0.5 significantly, something is wrong because your model is predicting backwards. Why? That would mean that you're giving the non-churns a higher risk than the churns more than half the time, and that's got to be wrong. So if you get away from 0.5 in the positive direction, things are starting to go right. I would say 0.55 to 0.6 AUC, it's better than random guessing, but it's really not good. And other data scientists are, on the stream will vouch for that. For churn problems, I would say the healthy range of AUC is from around 0.6 to 0.8. Because that means that your churn is predictable, but not too predictable. Above 0.8, you get into the danger zone where something might be wrong. 0.8 to 0.85 is extremely predictable churn. I consider that suspicious. Why? Because churn is usually hard to predict. People are random, man. People will not use a paid service for months and not churn. They forgot about it. And then you might have your best customer churn for no apparent reason. So churn is really random and it should be hard to predict. And I would even say that if you get AUC above 0.85, something is probably wrong. It's suspicious. Churn is not that predictable. Now I just showed you that this churn AUC is 0.995. That's really high. So now does anyone know what's wrong? Why is this suspicious? Well, I'll tell you in a few minutes. Yes, Insipidity, it's too good to be true. And if you're a data scientist, well, let's actually look at this code maybe carefully. Let's see. Not this one. The AUC code. Yes, Insipidity was training and test data not separated. He knew the answer. And we'll do it properly in a few minutes. So if you look closely here, I just reloaded the training data. This was the original training data. The dataset path. Well, I actually didn't make it clear. I kind of didn't show you. But that was testing on the training data. So we'll do that properly in a minute. But first I want to introduce a second accuracy metric so we can do two at once. Now, lift is another accuracy metric which is good for churn, and it's actually good for explaining churn accuracy to business people because they don't really get AUC. It's kind of complicated, or even more complicated accuracy metrics. AUC is about the hardest thing you can explain to business people, and I wouldn't explain many other accuracy metrics to them. Now, lift comes from business, and here's how it works. You again base your accuracy measurement based on you look at increasing risk of your customers, and then you look at those customers in the top decile most at risk. And you look at the churn rate in the top decile of your customers, and you compare that to the overall churn rate here. So in this case, again, the top decile is these top 5% customers. And again, we had 2 out of 5 of them really churned. So the churn rate in the top decile here is what? 2 out of 5. That's 40%. Now the overall churn rate in this example is 5 out of 50, or 10%. So in this case, the lift is 4. Now, so that's the ratio of churn in the top decile to the ratio of churn overall. Now again, if you had a lift of 1, or not again, but the point is there's a baseline or a random guessing lift, which is 1, which would mean you had the same number of churners in the top decile as in the overall. So now let's look at a lift calculation for XGBoost. That's listing 912. And we'll make a new configuration by duplicating this one. And this will be the XGBoost lift configuration. As you can see, I have a lot of these configurations from different fighting churn code that I run. So let's get into the lift calculation. And here we're actually going to look at how to calculate lift. You'll notice I didn't show you how to calculate the AUC. I just used a package function. But there was no package function for lift, so that was why I've written my own. So let's look at the lift calculation. As usual, start by reloading the saved model from a pickle. And once again, we will prepare the data. Split it into the prediction data and the outcome, x and y. And we call the predict proba function to get the predictions that come out of the model. Now, instead of using an sklearn function, I'm actually going to use my own function, calclift, also from chapter 9. Now, in the calclift function, the first thing I do is actually a little sanity check on the goodness of the data, of your predictions, really. Because if you have a failed model, a failed training, for a lot of different reasons, you might not get a lot of unique predictions. You might not even get any predictions. But if you've done prediction for a while, you probably have seen a case where you had something wrong in your model and all the customers had the same prediction. Now that would cause the lift code to crash. Because remember, we need to look at the top decile of predictions. So I have a simple check here that I just checked that there are at least 10 unique predictions. Then we'll go ahead and use the algorithm. Now in this case, there are many more than 10 unique predictions. You can see that there's a whole range of predictions. So the first thing I do is I sort the predictions by the predictions. Rather, the predictions with the outcomes. So I take the predictions and outcomes and sort them by the prediction, which is done in this Python list comprehension one-liner. So now I have the sorted predictions. The next thing I do is calculate the overall churn rate, which is simply sum of y true over the length of y true. So the overall churn rate here came out as 0.47. And we already saw that. The churn rate is around 95. So that's the overall churn rate. I mean, the churn rate is around 5%, not 95%. So next we find out the indice of the 90th percentile, which I call here I90, and that's simply a little integer division. So the 90th percentile is at the 22nd thousand example. So next I'm going to actually get the count of the churns in the top decile with this sum around my list comprehension. So there's 1143 churns in the top decile, which gives us a top decile churn rate of 45%. So now our lift is the top decile churn rate over the overall churn. And our lift is 9.77 in this case. And now I'll just let this listing continue because there's really nothing else happens. Now it just prints the result, and that's the end of the listing. So here, it says lift score 9.77. Now, that sounds kind of high. And it is, actually. If you know lift measurements, this is also too high. So you don't want... hey, where'd my explanation of lift go? Oh, I didn't include the slide on how good is too good for lift. Okay, well, we already went through this for AUC, but lift should not be this high. And there's a table in the book showing you what a reasonable lift should be. And really, 10 lift is really too high. Again, this is the problem because the training data and test data are not separated. And we just measured the lift of the XGBoost algorithm on the training data, meaning that was the data that was used to fit the model. Now, the reason these are so high is because of the possibility which is known as overfitting. We're going to now talk about what to do about overfitting. This is a pretty well-known topic for people who are familiar with data science. It might be new for those of you who are not. But the reason you don't want to test on the data that was used to fit the model is that for a model like XGBoost, it can really learn too much about the data. And it will actually memorize details of your training set, and then it'll have an artificially high accuracy on them. And the solution to this is to test the model and measure accuracy on data that wasn't used to train the model. Now, most people know that as cross-validation. And actually, I'm going to talk today about backtesting. And backtesting is a type of cross-validation that respects time, that it's sensitive to time. And so this is an illustration here of backtesting. So suppose, like in this simulation, that you have data from January through June. That's the simulation, January through June 2020. Now here's how we're going to test the model without testing on the data that was used to train it. We're going to divide the data into different parts, say 2-month sections, January and February, March and April, May and June. So first we're going to train the data on January and February and not any other data. And then we're going to test the data on March and April. And that way the test will be on examples that were not used to train it. Then you can do the same trick again. Move the simulation forward. This is like a historical simulation. It's not like a historical simulation. It is a historical simulation. So backtesting is a historical simulation approach to validating your model. And we'll go through the code for this in just a minute. So we get to test 2, and now we're going to use March and April to fit the model in this period. And then we're going to test the model on May and June. So you do like a rolling window of testing where you historically simulate what would have happened if I trained my model at the beginning of March and then used it in March and April. And then you pretend that you refit your model at the end of April and used it in May and June. And that is the backtesting procedure. Now, why do this instead of standard cross-validation? I'll just explain briefly. Backtesting was invented by Wall Street quants, people who work at investment banks and hedge funds. And they were using statistical models to predict the stock market. They've been using it for a long time. They started doing this back in the 80s and 90s. Before we had XGBoost, they were predicting the stock market with statistics. But what they found was that a standard cross-validation does not do well in measuring the accuracy of stock market predicting algorithms because the stock market is changing all the time. And you can have something like a recession, and if your model was fit before the recession, it's going to predict really badly during the recession or during a stock market crash. And if you do cross-validation without respecting time, you shuffle all the examples, the positive and negative examples. So cross-validation doesn't respect time, so it would be like the algorithm would be trained on a stock market crash before it happened, and then it would do better during the stock market crash. So they found that doing a random shuffle cross-validation actually overestimates the accuracy in comparison to a more accurate historical simulation, which is what backtesting is. So that's why for churn, I recommend backtesting and not cross-validation, because most churn problems are live business problems. You know, you're a real business and your environment for your business is changing in real time. You might have new competitors, there might be a recession, you might change your features of your product, and your algorithm is going to be subjected to all these things. And by doing the historical simulation, you'll get the most accurate view of your accuracy. Now, you're probably thinking, oh, that historical simulation, that sounds complicated. I just want to use cross-validation because it's easy, right? Well, good news is backtesting is easy too, because it's already in Python. So let's look at the backtesting of an XGBoost algorithm with the next listing for the day, 913. This will be another this is another extra in this stream. In the book, I demonstrate the basic backtesting algorithm with logistic regression. So this is a version of that demonstration using XGBoost. So once again, I'm going to duplicate my configuration. Oh wait, no, I already have I already had this one. All right, question, insipidity. Would this be considered a time series problem? If so, should time series models also be used during model experimentation? That's a good question. And it depends what I would actually answer that this really is a time series model, because our features are all time sensitive and we make predictions for customers at different points in time, or we use examples of customers at multiple points in time. Now, what you mean by a time series model, or most people mean by a time series model, are specific models where the past values of a metric come into the prediction in a particular way, usually with a simple multiplier. Like a linear time series model would be to make your prediction by multiplying by, well, let's look at our data set. I'm going to go and rewind in the data set for a minute and go back to way back earlier when we were talking about what's in the data set. So we have these metrics like per month, and new friend per month. But remember, like per month and new friend per month are measured on particular days. Let's look at the data set. So let's say we look at one account ID. Haven't done this before, but let's try, if you filter this data and we look at account ID, say only 56, just doing a little data exploration here in Excel. So you can actually see that for account 56, we made multiple observations of them, and we measured these metrics at multiple different points in time. In this case, we looked at account 56 on 3 different days. So there is this time series in construction of the data set. Now, in a standard time series model, I would use metrics like the likes per month on a particular date in the, how do time series models usually work? By, you're multiplying by a point in the past by a particular multiplier. So I don't use time series models like a Garch model. This is turning into a terrible explanation. I don't use time series models like a Garch model or those kinds of formal time series models because it's not really appropriate. Like usually a time series model is predicting one variable in terms of its own past values, but we're not trying to predict a real valued outcome for one thing. And also, generally, past observations of different metrics are very correlated with each other. So here I'm observing each metric at these month-apart intervals. And as you can see, these different values for one customer tend to be correlated with the past values. So all of these are reasons why I don't really use formal time series models. I think I went too much into the weeds on that. And let's go back to talking about backtesting. But you could do more formal time series modeling. So let's look at the backtesting and see how we do it. So I said before, let's remind everyone, what was I talking about when I went into the weeds. Like many, kind of smart people, I love to go into the weeds on particular subjects. So this was the idea of backtesting, that we're going to train on some data in January, February, test on March and April, then do it again after advancing time. And yeah, thank you for the appreciation and sympathy. I hope my in-depth explanation didn't just confuse things more. Oh well, I do my best. So backtesting sounds complicated, but it's easy in Python, as we will now demonstrate, because there's already backtesting in sklearn. They actually call it a time series split. So they don't call it backtesting. They have their own name for it, the time series split, as compared to a random split. I prefer the original name for this from Wall Street, which is backtesting. And I'm biased because I worked in a Wall Street company for a while. Also, I think time series split is more of a mouthful. So anyway, to do backtesting with an XGBoost model, we load and prepare our data as usual. And then we create the time series split object with the number of splits we're going to use. Here I'm only using 2 splits because in this simulated example, remember there's only 6 months of data. And this is using these 2 splits actually implies that we're going to refit our model twice in those 6 months. And honestly, for a real production, real live churn prediction, that's pretty frequent. Usually people don't refit their churn models every month. But anyway, so we create the time series split object. Now, I'm going to use the AUC and lift metrics in the testing, and I put them in a dictionary. For lift, it's not a standard accuracy metric, so I use an sklearn function makeScorer to wrap my own function in an object. So now the lift scorer is an object that I just created, and it wraps my function, as, in the sense of a wrapper, a container, if you're familiar with object-oriented programming lingo. The AUC is a standard metric, so I can add it by string. And I'm also putting in the log loss here. We're not going to talk about log loss today, because that's kind of conceptual. It's good for fitting your model, though, so you might want to learn about it. Then we create the XGBoost classifier, just as we did before. And next we create a grid search CV object. The CV stands for cross-validation, which we're going to talk about more in just a minute. Right now, we're going to do a backtest, but not a cross-validation, and I'll explain why in just a minute. But you use the same object. So I create the grid search CV with my model, with my dictionary of score functions, and with my time series split, which is here, TSCV. That's not a great variable name, but so we create the grid search with all of these objects, and then we just call the fit function. Actually, it looks like I call the fit function twice because I call it on line 22 and then again on line 24. Oops. Hey, very nice X. Thanks for following. That's a not safe for work screen name, but very good, nice X. So anyway, actually doing the backtesting is easy. You create the grid search object with your time series, and then you call it. And it's running right now. It actually takes a minute. Where's the console? So we're running it. And I think I'm just going to... Well, I think it's running right now. Okay, there it did. Now it finished running, and we have to run it again, unfortunately. So now it's actually fitting. And here I'm just going to save the result out to a file. Now let's look at the result of the backtest. And we'll see what it shows us. All right, here's in a CSV file. I saved the output of the backtest. And... let's see. It's all in one row, which makes it kind of hard to read. I'm going to copy it and transpose it to make it easier to read, and I'll also make it bigger any second now. So this is the output of our backtest. And let's look at what it tells us. All right, it tells us the mean time to fit the model is 1.6 seconds. Great. Let's look at the actual lifts. So here we have the test lift. Now those are the lifts on the data that it was not trained on. So that's the out of sample forecasting. And our test lifts are 3.4 and 4 and average 3.6. Now we can also see the training lifts, which means the lifts on the data that it was fit with. Now this gives us our 9.9 approximately. The mean is actually, 9.9. So that shows us the difference between the lift on the data that was used for fitting the model. We're getting like 9.9, but then on data that was not used, what would be new predictions your model would make, the lift was only around 3.76. So a lot lower, but that's actually still pretty good. Now let's look at the AUC. Well, here you can see for the training data, the AUC is 0.99, like we were seeing before. But on the testing data, the AUC is only 0.73. So that's actually, as you may recall, that's what I called in the healthy range. So actually, when you look at the test data, the lift of this model and the AUC are in a healthy range. So that's actually reassuring. So we were kind of worried. So it's fitting very strongly on the training data, but it actually doesn't do too bad on the test data either. So that shows us, the rest of this is more outputs of the back test, but we can basically skip that for now. So that shows us one result on back testing the XGBoost model. But of course, the other question people usually want to answer is, how are you going to make your backtesting model more accurate? Now that is the cross-validation part. All right, we did this one. Now cross-validation is about finding the best parameters for your model. And the parameters, also called hyperparameters really, are things like how many trees are in your boosting ensemble. Because remember, the boosting, XGBoost is an ensemble of trees. So how many trees should you use? Actually, you have to tell the algorithm how many. And another question has to do with how do you weight the additional trees in the ensemble? When you're correcting the errors, I mentioned that you have to correct the errors of your previous ensemble members. So do you make very aggressive corrections by applying a large corrective factor or a small corrective factor? Now, changing parameters like that will improve the performance of XGBoost. And if you're a data scientist or statistician, you're already familiar with this, but I'm going through it anyway, for those of you who don't know. So this is an example of how you cross-validate. You do multiple back tests with different parameters, and then you look at which one had the best AUC and predict the best. So that's where this is all going, actually. Is when you use an XGBoost model, you really want to do cross-validation. And when you're using XGBoost for churn, you want to cross-validate using the time series cross-validation or backtesting. Fortunately, this is also very easy in Python. So now we're actually going back to one of the XGBoost listings, which is in the book, 9.6. And this shows you how to cross-validate and to find the best parameters for an XGBoost model. All right, so back to 9.6. You're going to see some stuff in common here with the backtesting, but some differences. So let's see. This says it's the XGBoost cross-validation. I'm just checking. Actually, there's two versions. Actually, I want to do the regular one. We'll do that other version later. All right, so now we'll go into the code for XGBoost cross-validation. All right, as usual, we open up our data and split it into the X and the Y, which is the prediction variables and the outcome variable. Now, we also make a time series split, just like when we were backtesting in the last example. And we also make this dictionary of the score models that we're going to use. Lift, using the make score function, and AUC, which is a standard. Now, the difference is about to come up. we create the XGBoost model as usual, but now I'm making a dictionary of test parameters. And these are going to be all the different parameters that we're going to test. I should actually start running this code because it takes a while. I'm going to run this and then I'll, well, go back to the explanation. So there's 4 parameters: max depth, learning rate. I'm going to start running it and we're going to look at the output because this actually takes a little while to run. So the max depth is the depth of the trees, because remember the XGBoost is based on decision tree algorithm. The number of estimators, n estimators, is how many trees the algorithm should try to use. And here I'm telling it to use either 20, 40, 80, or 120. The learning rate has to do with how aggressively it tries to correct the errors. And so the lower the learning rate, the less aggressive the error correction is going to be. And the higher the learning rate, the more aggressive the error corrections are going to be. And that can be good, but it can also lead to more overfitting. So, and lastly, the minimum child weight is actually a way of also preventing overfitting by not letting any child, which means any tree in the ensemble, have too low a weight, even if its error correcting properties were not that great. So it's because it's basically been found that XGBoost is too good at predicting these outcomes. Hey, Danny Spark, welcome back. I'm glad you made it while I'm still streaming. I don't know if you've been here the whole time. Danny was one of the witnesses to my horrible crashing stream last week. But glad you made it back. I'm kind of mostly through the stream at this point. We're talking about XGBoost cross-validation. And I think it's still running, actually. Wait a second. Is it crashing? Can't tell. Is it crashing or what? I think it crashed. A lot of times I have weird shit happen in the debugger here. I'm going to kill it and just run it from the top without the debugger. Yeah. All right, now it's working. Sorry, so that whole time it wasn't really running. It was crashing in the debugger. So sorry for that. The debugger is not always reliable. But I was explaining about the test parameters. So now as you can see here, we have 4 parameters that we're testing: max depth, learning rate, number of estimators, and minimum child weight. And I also happen to use 4 different values for each of these parameters. So for the depth, I'm testing 1, 2, 4, 6. For the learning rate, 0.1234, etc. So 4 parameters, 4 different values, we've actually got 256 different combinations, because that's what the cross-validation grid search means. It means you make a grid of your parameters. And if you have 4 parameters, it's a 4-dimensional grid, which you can't really picture, but it doesn't matter, still a grid. So that's why we've got 256 candidates. And there were 2 folds. That was my number of splits. They call a split is called a fold. So this is why, well, it's still running. So we're doing 256 times 2, 512 different XGBoost model fittings. And as you may recall, each one took about a second. So this might take several minutes to run. So after calling the fit method, I just save the results in a data frame. I also sort the values of the data frame by the test AUC, so that the best or highest AUCs will be at the top of the result, and then we save it. Now, there's one other thing we're going to do with this cross-validation, which is we're going to save the best model. Because we test a lot of different values for the parameters, we're going to figure out which is the best one. And here I say refit. When you pass this parameter, it's going to find the best model for you. Danny Spark asked, do you know any technique more efficient than GSC? I tried it in medium-sized data set, 400,000 rows, and it was taking forever. Well, I have also used XGBoost on big data sets with a lot of rows, and the truth is, sometimes it takes a while, especially your cross-validations. It can take hours. The best advice is to run it in the cloud. We use AWS at my company. at both my current company and my last company, we use AWS. And when we had a big XGBoost cross-validation, we run it in AWS. Now, one of the things I have not explained about XGBoost is that it works well in parallel. So it's a highly parallelizable algorithm. Let's see. I was going to try to check now and see if mine's running in parallel, and indeed it is. So I just opened up my activity monitor to show you, and you see all these Pythons running. That's my XGBoost algorithm running in parallel. So one of the great things about XGBoost is that it's highly parallelizable, so make sure that you are taking advantage of that by running your XGBoost algorithm in parallel. And if you don't have enough speed on your local system, run it in the cloud, and then you can really scale it up. I've done big data sets. We had, at my last job, we had data sets with hundreds of millions of rows, and we would use XGBoost. And one XGBoost fit, it would take a couple of hours, which isn't too bad. But then when you do cross-validation and you're doing hundreds of XGBoost fits, that's where it really kills you. So that's when you really want to be running it in the cloud. Here, this is a great way to see when my algorithm ends. Still running. So I have to find enough stuff to talk about while the XGBoost is running. For model mechanics, what are your thoughts on recall sensitivity, true positive rates? I actually don't like recall sensitivity. I actually generally use the AUC as an accuracy metric, and also the lift to explain it to people. And also I'm getting more into using log loss. And what's good about these metrics that I'm describing is they're all based on the real valued output, which is the probability of the outcome. I don't like actually using recall sensitivity and also accuracy, because all of those algorithms require you to categorize your points into true or false, right? And you might be thinking, but don't you have to categorize them into true or false? Actually, in my experience, looks like the XGBoost algorithm might be finishing. I'm seeing some signs of life. Yep, looks like it finished. So anyway, I was explaining how I prefer to use accuracy measures that are based directly on the real valued output, because then you don't have to pick the thresholds. And also, the truth is, your use cases for churn predictions don't usually use true or false predictions. Like if you go to the marketing department and give them a list of trues and falses, it's actually not that helpful to them, because they want rankings. They're going to run a campaign against a certain number of customers. And what if your true and false predictions? What if you predict 194 churners and they're like, we want to run our campaign on 100 customers. So 194, well, how do you pick the 100 to run the campaign on? You use the probability output. Anyway, so that was kind of going into the weeds. So now we have saved our model in a pickle, and we've also saved results and predictions of the model. Let's look at the output of the cross-validation. The histogram you can kind of see here looks pretty much like the others, but we want to look at the cross-validation results, which is in this file. And this will show you how we did. Now remember, we tried 256 different values of the parameters in the cross-validation. So that's why this version has 256 rows. I'm going to freeze the top row and then we can look at it some more. So these are the same columns as we had when we were doing the backtesting, except there's a few new columns. Now we have these new columns here, which give you the values of the parameters in each test. So this first test used learning rate 0.2, parameter depth, max depth 1, child weight 12, number of estimators 120. And this is actually the best, because remember, we sorted them by the AUC. So this has the best AUC, and that AUC, which you can kind of see here in the small font, is 0.8. Now I'm not showing the test The training AUCs. That's the in-sample AUCs in this file, because those are mostly interesting when you're demonstrating what the difference between training and testing is. Now that we know we have to look at the testing accuracy metrics, I don't even bother including the training accuracy. They're probably like 0.99 anyway. Maybe lower. But anyway, so we found that the best accuracy is 0.8 and the best average lift is 4.5. Now if we go down, remember there are 256 different parameter values here. The worst one at the bottom has lift of 3.5 and AUC of 0.71. So actually those are very close to what we were seeing in the default model before we did any cross-validation. Let's see, so Danny Spark was reading about Bayesian optimization technique, which is supposed to be faster to tune the parameters. Well, I'm actually not sure about that one either. There are a lot of great boosting techniques coming out, and I'm pretty much using XGBoost Classic, which means it's not classic because it's only a few years old. But I'm using kind of the standard or most well-known XGBoost. There are a few kind of like more specialized versions of boosting that follow similar principles, but I don't really know. So XGBoost is generally considered fast because it is very parallelizable. I mean, it was much faster than what came before it. But then, of course, people say, oh, here's a fast algorithm that I'm gonna cross-validate a lot of parameters. So people will always cross-validate as much as their computing architecture will allow them. And so one thing you can always do is maybe don't cross-validate so much, because the truth is, would this really have been so much worse if I had only cross-validated 100 combinations instead of 256? Who knows? But anyway, this is how you do cross-validation. Now, the other outputs like the the histogram of churn probabilities, they look pretty similar in this. But now we know that we have the best accuracy on the out-of-sample testing. So let's see. Now what are we going to do? We're going to go back, now that we've actually also resaved the model. So now we want to go back and recheck some of these other things that we were doing earlier. So let's look again at the AUC on our new model that I saved. Oh, I see. So Bayesian is supposed to do the grid search faster. Okay. Maybe it's a smarter grid search where it uses information to pick rather than just blindly trying every possible combination. Now that makes sense. Maybe I can do a new stream on those sometime. So let's rerun, let's see, the 9, 11, and 12. Let's see. I have this redo analysis. I actually prepared for this. Although, yeah, so we've resaved the XGBoost model from that other listing. So like I was saying, this model is also saving the best estimator in the pickle file. So that's my new saved model. And I'm going to rerun the Shapely analysis and the AUC and lift, and we'll look at them real quick. I'm not going to go back into these code samples because we already looked at these code samples earlier in the stream. Sorry, Danny, or those of you who joined later, but you can rewind and watch it later. So the first thing we can see is now that I've resaved the model, the AUC is actually much more reasonable. So now it's saying AUC 0.81 and lift 4.88 on the data. And I also resaved my Shapely explanations in this file. Now this actually looks very different than the explanations that we saw with the original model. So this is important. For those of you who didn't see the earlier version, again, rewinding the stream, but we had an overfit version of XGBoost earlier, and it looked very different than this. This shows much more of a tree-like behavior, where you can see that the points are discretized into certain groups. Let's zoom in. I explained how to read these plots before, but I'll briefly go through it for new viewers who haven't seen shapely explanations of decision tree models before. So each row shows you the contributions for one variable or feature. And the color, each point, this is actually made up of a lot of the individual points. Each point is the contribution on one prediction of this feature. And then the points stack up when a lot of points have the same contribution. So this is showing this, and then the color is the feature value high or low. So this little stack shows you that these are a bunch of examples where high values of message per month were associated with low churn. And that's because on the x-axis we're showing the impact on the model value. To the left of the 0 line means reducing churn. To the right of is increasing in churn. So you can see the highest values of message per month reduce churn, and some lower values too. Similarly, for new friend per month, the highest values are reducing churn. And that goes on for the first top 3 metrics. So the metrics are also ordered in order of importance, with the most important at the top. So message per month is the most important, new friend per month is less important. And you can visualize the decreasing importance because you see how the points are getting closer and closer to the 0 line as you go down. So the least influential metric was new friend percent change, and you can see that all the points basically have no impact from this metric. But as you go up in the plot, you see which points have more impact. Now what's great about the Shapely method or shape method for explaining these models is you can actually see the sign of the influence and the magnitude of the influence. So the 4th most important metric, ad view per post, you can actually see that high values on this metric contribute to increasing the churn probability. And then the lower values on this metric give you reduced values of the churn probability. And that is one of the great things about this method of explaining XGBoost in comparison to the earlier methods, just the importance plots that most people use, because it actually gives you the sign of the influence, the direction of the influence, and the magnitude of the influence. Now, I don't know, I went through the shape code earlier in the stream, maybe before some of you joined. We could go through the shape code again real quick if anyone on the chat says it. But for now, I'm just going to show you this is a lot different from what the explanation of the overfit model looked like. So this is actually, for this problem, a healthier looking explanation. And it shows that we're using fewer smaller trees. I think we're using smaller trees in particular. I believe when we looked at our best parameters, the max depth is only 1. Hell, that's a very short tree, but we're using a lot of them. So we're using the best hyperparameters in this case were a lot of small trees, which contributes to the shapely explanatory visualization having this kind of cut apart, disjointed view. All right, so what's left? There's just a few more things left in this stream. So we rechecked the AUC and the lift and the explanation. Ooh, machinelearningmastery.com has a good article on explaining and implementing Bayesian optimization. Okay, and that's for Danny Sparks' question. Thanks, Insipidity. All right, now, here's a good part. XGBoost versus logistic regression. Everyone wants to know, is machine learning more accurate than regression? Well, of course, the answer is yes. I'll quickly review the listing for cross-validating regression. That was 9.5, and I did that in a previous stream, but we'll do it again so you can see how easy or how similar it is to cross-validating XGBoost, and then we can see which is more accurate. So I think I have a configuration for this. Let me check, actually. It's got to be listing 9.5, regression fit, no. Oh, here it is, regression cross-validation. Chapter 9, listing 5. Now this code is very similar. I'm just going to run it, and you'll see it's a lot faster. You'll see it's a lot faster. It's also, well, it's done. That was it. That was the cross-validation of the regression. So it's a lot faster, but it has the similar steps. We prepare the data, we do a time series split, and we use the lift and AUC score models. Now there's actually only one parameter to test. That's one reason it's a lot faster to cross-validate regression. And it's also a faster algorithm to train. And the rest of this listing is basically pretty similar to the cross-validation of the XGBoost. So I'm not going to bother going into the details, but let's look at the output. Let's go straight to the output and see how accurate was the cross-validated regression. Try to compare them side by side. I can do that by lowering this down after I move it over. So the lift that we got from the regression algorithm shown here, the mean lift was 4.4, and the XGBoost algorithm, we had mean lift 4.5. So XGBoost is more accurate by 4.4 to 4.5 in the lift. And when we go over to the AUC, the mean test AUC of the regression algorithm was 0.78, and the mean test AUC of the XGBoost algorithm is 8.0. Hope you can all see that. So 0.78 to 0.80. Now let's actually, I have this illustrated more clearly here on a slide. So this is XGBoost versus regression in both the simulation and a bunch of other case studies that I've done. So this is the result we just looked at, where the social network simulation, we got 0.78 accuracy with regression, reg for short, and 0.8 accuracy with XGBoost, shown in this column. So that shows about 2% increase. Now, is that good? Is that a lot? Maybe you were expecting more, but actually 2% increase in AUC is pretty good. Because earlier when I was talking about AUC, I explained that the entire range of AUCs that you really see is like between 0.6 and 0.8. Like 0.6 is a bad churn model, 0.8 is a good one. So the entire range, or really the best, is around 0.8. So the entire range of plausible values is from 0.6 to 0.8. So a 0.02 improvement is actually pretty good. And 2% improvement in AUC is nothing to sneeze at. Now let's look at some other examples. For case study 1, XGBoost it was 0.71 to 0.69, so that was a 0.02 improvement. Case study 2, 0.77 to 0.82. So that's a 0.05 improvement in AUC in that case study. That's even more significant, and that's what you'd like to see. And case study 3 had the biggest improvement, 0.06 improvement, XGBoost compared to regression. So that's a realistic difference that you should see in XGBoost versus regression. Now in lifts, we're seeing differences like about 0.5 improvement in lift or less, 0.2 to 2.6 to 2.8, 3.5 to 4. This one only a little bit improvement in lift and a much higher improvement in AUC. But I'll tell you, the AUC improvements are what you're looking for more. As I explained in the book, the lift metric, it's kind of unstable. It's good for explaining your model to business people, but it's actually not that good for fitting your model. So focus on AUC. But this does show that in every case, XGBoost is more accurate than regression by a few percentage points in AUC, from 0.02 to 0.06 in these examples. Now, let's ask another interesting question. Feature engineering. Because someone asked earlier about feature engineering and if we were going to talk about it. So Insipidity, I think, asked the question, or someone asked the question about feature engineering. So now here's a question. Does feature engineering help? So in some of my previous streams, we looked at feature engineering, and we looked at both making simple metrics and making more advanced and complicated metrics for features. So it's natural to ask, does that help? Did it make a difference? So first I'm going to review what are the simple versus the advanced data set and metric. So the simple data set has only per month averages, like per month, new friend per month, post per month, etc. And so this is the basic data set that was used earlier in the book, if you recall. If you read the book, that is, or if you watched some of my earlier streams. Then in later chapters, this was actually in chapter 7, and in later streams, we added metrics like ratios and time-based metrics. And these were the things like ad view per post, like per post, post per message, also the days since the last new friend, etc. So those are what we call the advanced metric data set. Now you can actually use the code in the book to rerun the simple metric dataset with XGBoost. And that's version 1 of the XGBoost cross-validation. And I'll demo that real quick. I think it's going to be the last code listing. I'll just show you how that works. I think I'm going to go back to my XGBoost cross-validation configuration, which was Chapter 9, Listing 6, and I'm just going to add the argument version 1. And now this is going to be on a much smaller data set, which is the simpler data set. And I'll run it now. We could look at the listing again, but since we just looked at it a few minutes ago, I think we won't bother. This should be somewhat faster because the data set has about half as many features or metrics in it. But I think I'm just going to go straight to the answer now that I showed you how to run it. And that is shown in this slide. So there's actually some difference with the basic and advanced metrics. And I'm showing it in this kind of cluttered slide. So what you find is that on the left, this is basic metrics, and on the right, this is advanced metrics. Now remember, I just showed you that XGBoost only made a little improvement over regression. That was that 0.78 to 0.8, and that was using the more advanced metrics. However, if you do this exercise of running regression in XGBoost on only the more simple and basic metrics, you actually find that XGBoost does a lot better, at least for the simulation. Now, with only basic metrics, XGBoost improves the simulation AUC from around 0.67 to 0.77. So that's a big 10% increase in AUC. So if you use only simple metrics, you might have more to gain from using machine learning and more to lose from using regression. However, if you do feature engineering, you will often find less to gain from machine learning, which is what's shown here. So when we use the advanced metrics, XGBoost only improves over regression a little bit. Now let's look at more case studies. Case study 2, this is a case study with real data. And what you can see here is that, again, for basic metrics, XGBoost improves significantly over regression. And then the regression with the advanced metrics is about as good as XGBoost with basic metrics. And then XGBoost with the advanced metrics improves even more, actually. So that's actually what we saw in simulation too, is that regression with basic metrics, that's this AUC around 0.78, is about the same as, regression with the advanced metrics is about the same as XGBoost with basic metrics. And then using the XGBoost with advanced metrics improves it even more. Case study 1 shown up here actually shows a case where the advanced features don't even really help, which is interesting. Usually they do, and that's what you're seeing in most of these case studies. But not in every case study will making more advanced metrics help. Unfortunately, the only way to know if feature engineering is going to help you is by testing, which is why I recommend doing feature engineering. And in the previous streams and in the book, I give lots of good tips on how to do your feature engineering. Lastly, in case study 3, once again, pretty similar to the standard finding, where regression with advanced metrics, here it's a little bit better than XGBoost with basic metrics. And of course, the best accuracy, well, not of course, but as usual, the best accuracy is XGBoost with advanced metrics, or using feature engineering to improve over only your basic metrics. So those were case studies in feature engineering with XGBoost and regression. And I think that's it. Yep, that's actually all the content I had prepared for this stream. It's already been 2 hours, which is a pretty long stream for me. I knew this was going to be a big one, but there was a lot I wanted to cover. And I didn't just cover what was in the book. I did a lot of cool stuff demonstrating overfitting. I don't even really demonstrate overfitting in the book. I just show people the right way to cross-validate. All right, here is the summary of the stream, the closing. So, fighting churn is about targeted interventions, improvements, engagements, and supporting your customers and having a good pricing plan that makes your customers want to stick around. XGBoost is a state-of-the-art machine learning algorithm. You should definitely know about it. It is very popular. It dominates in Kaggle competitions and things like that. The shape method allows you to interpret XGBoost predictions, and it makes XGBoost really much more interpretable than it ever used to be. Honestly, I said earlier in the stream, in the book, well, when I wrote the book, I didn't know about the shape method. So I said, use logistic regression to interpret your data because it's easier. You can look at the coefficients. And at that time, I didn't even advise people to try to interpret XGBoost because personally, I always found those explanations, so unsatisfying. But with the shape method, you should definitely use it to interpret your XGBoost. Now, hyperparameters are parameters that determine the shape of the trees and the operation of the algorithm. Now, they say hyperparameter to distinguish it from the cut points of the trees, which are the parameters that are found by the algorithm. So, to get the best hyperparameters, you need to use cross-validation. And not just cross-validation. Well, first I said without cross-validation, XGBoost will overfit. That means it's going to do really well on the data that you fit the model with, but worse on other data. But don't just use cross-validation, you should also use backtesting, which is a real-time market-sensitive simulation. Or I say it's sensitive to the market conditions when your data was generated. Now, Python calls backtesting time series sampling or time series cross-validation. I like to call it backtesting because it's just, it's just easier to say. And it's also the original term that was invented by the Wall Streeters who started doing those kind of simulations. Lastly, feature engineering makes XGBoost more accurate, usually. As I said on the last slide, this one out of 4 case, actually, feature engineering to get advanced metrics did not really help the accuracy. But in most cases that I've worked on, doing your good job on feature engineering will improve your accuracy, and you should definitely do it. All right, I think that's it for the stream today. If no one has any further questions or comments, I will give you my exit by reminding you I live stream at 2 Pacific. Insipidity, thank you very much for joining me from East Asian time zone, like 6 a.m. or 7 a.m. for you. And also, if anyone else is out there in Australia, whatever, where it's earlier for you, thank you. Also, anyone who's joining me from Europe, I don't know, occasionally Maddie Two Shoes from Central European time will join me, but I know it's like 1 a.m. over there now. Danny Spark says, awesome, I will go back and watch what you missed. Well, thank you. Have you ever done a stream to predict the time of churn? Wouldn't that be as important as predict the churn? I don't exactly predict the time of churn because all of these forecasts have an implied timing, which is when you predict churn, it's always implied the customer is churning within the next month. And that's actually going back to the data set. Whoops, let's look at the data set real quick. I think I still have it open. So remember, the data set is composed of observations of customers on a particular date, and that's the date when these metrics were measured. Now, the outcome is churn is referring to whether they churned in the subsequent month right after the time when these metrics or features were measured. So the timing is implied in the model that we're predicting the probability that this customer will churn in the next month. So that's the first thing to know. So there is an implied timing in every prediction. Now, I don't propose or suggest that you predict the exact time a customer will churn within the next month, because the churn probability of most customers is pretty low. As you can recall, when we looked at these histograms, let's see, this is not the histogram to look at. Let's look at, not this. I wanted to show you churn probability forecast histograms, which look like this. So most customers have pretty low probabilities of churning, less than 10%. So it's not actually that meaningful to try to predict, I think, the exact time. Oh my God, someone was raiding with a party of 22 right when I'm finishing my stream. That's terrible. Out in one. Oh, sorry people. Hello, joiners. I'm really sorry to tell you, everyone who's just joining my stream, but I'm kind of wrapping it up. I mean, if you want to hear about data science, I could start over. Mr. Scythe, thank you for following, and thank you for Out in One for rating. Are all the raiders interested in data science? Because we're not gaming here. This is a data science stream. And I was just answering, yeah, shit, the timing. I'm just wrapping up. But I was answering the question. I'm answering a question, so I'm kind of in chat mode. Would we predict the time of churn? Now, the problem is that predicting the time of churn, oh cool, development stream. Well, this is a data science stream, and I'm very happy to have you all here. So I'm answering the question about, we don't really predict the timing of churn because, number one, there's an implied time horizon in every prediction. We're predicting for within the next month. Then there's a low probability of most people churning. So usually the probability of churn is, in this case, less than 10%. So predicting a particular time for someone to churn, oh my God, you've been developing for 12 hours. Whew. All right, I'm going to shut up about streaming for 2 hours because I've only been streaming for 2 hours. So I guess if you guys want to learn some data science, I could go back into it. But anyway, still answering the question about do we predict the timing of churn? Not really, because it's very hard to predict the timing of churn, and also the probability of churn is low. Now, you could come up with an expected time of churn for every customer, which is actually just 1 over the churn probability. That was actually explained in my stream last week, that the expected length of time that a customer will last. Oh, thanks for following, Out in One. Hope you can join me again sometime after you haven't been development streaming for 12 hours. But so anyway, what was I doing? I was explaining why we don't really this was the summary for today's stream, and we were explaining why we don't really predict the time of churn. Although in my previous stream I was explaining that 1 over the churn rate is the expected lifetime of any customer. So if a customer has a churn probability of 10% per month, and these are monthly churn predictions, their expected lifetime will be 10 months. Similarly, if a customer has an expected a churn probability of 5%, their expected lifetime is 1 over 0.05, or 20 months. And I actually went into all of this in gory detail in last week's stream, so you can find it out there. So I don't really predict the time of churn. We predict the probability of churn per month, it's in the next month is kind of what that means. And you can predict the customer lifetime using the churn probability. So that's why I don't really do it. All right, and Insipidity had a question. A business request for expectation future LTV. Future LTV is lifetime value. I built a model. Is this request even possible? Oh yes, Insipidity. This is all coming together. You gotta watch my stream from last week. My entire stream from last week was a in-depth explanation of lifetime value forecasting using churn forecast probabilities. So basically, I'll just do a simple example of this. Like, let's say, remember we were looking at some churn forecasts earlier. Where are the forecasts? This is the back testing. All right, I closed up the forecast. Let's look at some churn forecasts real quick. And I can show you churn lifetime predictions. So here's the predictions from the XGBoost model for these customers. And I just saved it in a file. And one column is going to be my retention probability, and the other column is my churn probability. So now expected lifetime in months, because these are monthly churn probabilities, that's the implied horizon, is just 1 over the churn probability. So that's super easy. So this customer with a 2% churn probability is expected to last for 50 months. And this customer with a 3% churn probability is expected to last 31 months. Now, this is actually an important thing I go into last week. For low churn probabilities, you've yet to build a model. Hang on, you're misreading my message. You've yet to build a model for LTV. Well, you don't, what I'm saying is you don't need to build a special model for LTV. The way you do LTV is by predicting the lifetime of the customer. So now, if my customer is expected to last 50 months, let's say it's $10 a month, the LTV is just, $10 times the lifetime. Well, more specifically. So LTV is actually predicted from a churn model, not from a special LTV model. So Insipidity, if you haven't fit a model, get up to the later chapters where you do the churn prediction, and then you can do LTV. Now, this is showing a caveat. You need to put a maximum, like a reasonable maximum. So I would say that the expected lifetime for these customers is the lesser of, let's say, 3 years and the churn probability. So now we're not going to predict that anyone's going to last, like, even people with very low churn probabilities, you don't predict that they're going to be your customer for 100 years. You just kind of go through it this way. So this is the point being that once you have a churn prediction model, you already have a lifetime value model. So does that make sense, Insipidity? And again, I did this, or does that answer the question more accurately? So I went into a lot of details about how you use the churn prediction to do lifetime value in the last stream. We could even bust it out now that there's viewers who joined rated from the other stream. But anyway, I think I'll probably just wrap up the stream. And I'm so glad you guys joined me. I'm really sorry that it was so late. But I kind of went through everything already today. Everything I had prepared. So, for those of you, assuming there are no more questions, and no one's gonna, we're not gonna go into the weeds on anything else, I normally do stream at 2 p.m. Saturday. Okay, yes, that did answer the question. Yes, get up to chapter 8, and it'll explain all about lifetime value and using a churn model to do it. So, definitely possible, not even that hard. So my streams start at 2 Pacific Saturday. I've been going just over 2 hours now, which is about as long as I usually stream for. I want to get on to doing some other things this afternoon. It's still afternoon for me, of course, and I've got the rest of my Saturday ahead of me. So let's see. Usually stream Saturday at 2. Please join me next time. Please follow me to get the updates of when I'm streaming. Also, if you're a YouTuber, and I don't know why you would be, I also put all my videos on my YouTube channel, also Fighting Churn with Data. So easy to find, but the Twitch crowd usually doesn't care about this. But if you have friends who are YouTubers, you can always point them to it. Now, all of this content is based on a book that I wrote. It's been out for a few months, Fighting Churn with Data. Wow, Out in One, thanks for saying I'm a cool dude. I'm going to check out your stream too, because I don't know, if you like my stream, I'm probably going to like yours. So yeah, I'll try to raid you next time if we get a chance. But yeah, so I stream content about data science, and it's mostly based on this book. Although as you saw today, I was adding a lot of content to the book. Front-end stuff, okay, that's cool. So like UI development. There's also a discount code if you want to check out the book. Well, that's for buying it from my publisher, of course. All right, correct, UI. Well, it's not really my cup of tea, to be honest. I'm kind of a back-end data guy, obviously, since, I don't know, I do data science. But so here's where you can find more about Fighting Churn with Data. It's the basis for all this content. Also, please keep in touch with me. Connect with me on LinkedIn. Basically, I'll connect with anyone on LinkedIn if you tell me that you're interested in Churn or you watch my stream. Happy to connect on LinkedIn. Also, please follow me on Twitter. That's where I'll give all the updates about when I'm streaming, what I'm streaming, and other random interesting things that I find about Churn and data science. I don't really tweet off topic, to be honest. I'm not going to tweet about my personal life or politics or anything. Oh, right, you can't connect on LinkedIn without inputting my valid email. Right. Well, here's what to do. I'm not going to post my email for everyone, but you can message me on Twitch. Twitch message me, and I'll send you my email. How about that? That's what I do, because I don't want to put my personal email here on a Twitch stream. Yeah, you guys need an email. Okay, I'll Twitch message both of you guys with my email so we can connect on LinkedIn. Definitely. So yeah, I also respond to messages on like Twitter and Twitch eventually. I respond to LinkedIn messages pretty quick. So yeah, so connect on LinkedIn. I'll message you guys my email later. Absolutely. So yeah, that's really it. Thank you for joining. I think my last slide is going to say next stream. Actually, next week I'm going on vacation, so definitely no stream next week. But in 2 weeks, I should be streaming again, and it will be demographic data analysis. So we haven't really touched that yet. In case you noticed, in our data set that we were looking at, where's the data set? We have only been looking at what I would call behavioral metrics, like likes per month, new friends per month, posts per month. These are all the types of things that people do on the service. But we have not been looking at demographic data, which is things about like where people live or how old they are. Or if you're analyzing churn for companies, you use what we call firmographic data, which means it's information about companies, like what industry they're in or how many customers they have. Cool, so that's going to be the subject of next week's stream. And yeah, everyone else, have a great rest of your weekend. I don't know, let's see, so we've got people still streaming. If anyone still wants to stream some code, we could see who else is active. Because I know Out in One just rated over here. Let's see if any other coders are currently live. I follow various coders. Let's see. I sometimes follow Anthony Wright's code. And he seems to be doing stuff now too. So I say, first I'm going to, anyone who's still with me. Oh, and thanks for following Producer Wolf. That's a cool thing. So I say let's raid over to Anthony Wright's code. And everyone who still needs their tech fix this afternoon, maybe it's the later in the evening for you, Hello, you need help on machine learning. Oh, damn it, you just joined and I'm like finishing. Well, now that you discovered my channel, I've got lots and lots of videos on machine learning. But I've been live for like 2.5 hours now, and unfortunately, yeah, I got some other stuff to do. It's Saturday afternoon. So please come back again, Producer Wolf. I'm so sorry that I'm bailing right when you joined and followed. But so I say let's raid. Yeah, maybe, okay, so I was saying just a minute ago to connect with me, I really should do a Discord for all this. At the moment, I don't have a Discord, but Producer Wolf, connect with me on Twitter or Twitch. Also LinkedIn. Although, as some other people were just pointing out, you need my email. So Twitch message me and I'll share my email. Oh, you have your own Discord server. Cool. All right, and do you talk about machine learning? Your YouTube channel link on your Twitch summary. I should. That's a good point. But why would you put a YouTube channel link on a Twitch summary? Because well, in my case at least, all my videos are highlighted on Twitch. So if you're in Twitch, you could just watch it right there. So there's something to think about. Why do you link to YouTube from Twitch? Anyway, I guess for people who would rather watch on YouTube, I don't know. Oh, cybersecurity is Producer Wolf's channel. Interesting. All right. So, like I said, that's how to connect with me. Thank you for joining. Next week, we'll be talking about demographic analysis of churn data. And I'm going to just raid us over to another coding stream, which I have occasionally watched. Seems to be hacking away. So let's go. All right. We'll send you guys my email so we can, LinkedIn connect. And get ready for a little raid going on. Thank you again, everyone who joined me. So, yeah, have a good week or good rest of your weekend, and maybe watch some more coding stuff on Twitch. I'm out.